Okay, today we are going to study the normal distribution. And this is the single most important probability distribution you will ever learn in statistics, I would say. And that is defined by this density function. But before going into the details, let me explain why this distribution is so important. The first reason is, in practice, experimental errors are often approximated by a normal distribution. So if you do any experiments, it is usually the case that errors are, experiments always contain errors. Errors are nicely approximated by normal distributions. And second, many probability distributions can be approximated by a normal distribution. For example, binomial distribution and Poisson distribution. They are discrete probability distributions, but when the number of samples are large, then they can be approximated by a normal distribution. And third, actually this is the most important reason, we have the so-called central limit theorem. Maybe you have already heard about this before in high school. So that says the sum of many random variables tends to follow a normal distribution. So if you have many probability distributions, random variables, like x1, x2, x3, and so on. So if you define this, then this sum follows, well, it will be very well approximated by a normal distribution with some parameters. Okay. And fourth, many important other distributions in statistics are derived from normal distributions. And we are going to learn some of these such distributions in later lectures. And the final reason, normal distributions have some nice properties that make them easy to deal with analytically. So, for example, the sum of two or more normal random variables are again normal random variables. So this is a very nice property, and it makes it very easy to deal with by hand without using computers. Now let's go back to the definition. The normal distribution or it's also called the Gaussian distribution. Is defined by this density function. So 1 over square root of 2 pi sigma exponential x minus mu squared to sigma squared. So we have two parameters. Let's see, this sigma and this mu. Okay, and this variable x can take any real values. Okay, and this parameter mu is any real number, and the parameter sigma is also a real number, but it has to be positive. Okay, so since this is such an important distribution, you must memorize this density function. Okay. And when a random variable x follows the normal distribution, we write like this: n mu sigma squared. So this means this random variable x follows the normal distribution with parameters mu and sigma squared. Okay. In particular, when mu is 0 and sigma is 1, then we call this normal distribution one as the standard normal distribution. Normal distribution. Okay. So this is called standard. Okay, this one is standard. And the density function looks like this. So when so mu is 0 and sigma is 1, it's this purple line. Okay. So this is symmetric around 0. So this is x equal to 0. When mu is 0 and sigma is 0.5, then the distribution is still symmetric around 0, but it's narrower. Okay. So actually this sigma is the standard deviation of this distribution. So when sigma is small, then the standard deviation or variance is small. So this width becomes smaller. Okay. And when mu is 3 and sigma is 1, then the mean is shifted. So previously when mu was 0, it was this distribution was symmetric around 0. But when mu is 3, mu actually represents the mean of the distributions. So the mean is here, which is actually 3, and it's symmetric around the mean. But this standard deviation is the same as this one. Okay. Let's see some properties of the normal distribution. I think you have tried this integral before. X squared to dx. So the value of this integral, if you try to calculate, is square root of 2 pi. So if you remember the density function for the standard normal distribution, that is this 2 pi exponential x squared over 2. So this is the density function for the standard normal distribution. Okay, so if you divide both sides of this equation by square root of 2 pi, then you can easily see that the integral of this density is equal to 1, right? Just as expected. Because it's a density function, so if you integrate all over the space, then it should be 1. It's normalized. So, using this result, it is easy to see that, but you should try yourself, this integral So this is the density function for the very general normal distribution with mu and sigma. So if you integrate this, this should be 1, right? All you need is to do some variable transformation. Okay. And it is, let's consider now expectation value. Okay. So first, let's try this integral, the standard normal distribution. So x exponential x squared over 2, and that is 0. So that means the mean of the expectation value of the standard normal distribution random variable is 0. Okay. And then try this one next. X squared. So you can calculate this integral by integration by parts or something like that. And you should have this is equal to 1. Okay. But the mean is 0. So this is actually the standard variance of the standard normal distribution. So that means expectation value of the standard normal distribution is usually denoted by z. So z follows the standard normal distribution. Then the expectation value of z is 0. And the expectation value of z squared is 0. But therefore, the variance of z is, no, not 0, sorry. This is 1. So the variance of z is 1. So this minus this squared is 1, right? So we have these results. And using this, now you should be able to show that the expectation value of the general normal distribution actually, maybe you can write this. Oh, maybe I should just calculate the expectation value. So this one 2 sigma squared. So if you calculate this, you can see that this is actually equal to mu. And similarly, if you calculate the variance, so since this is the expectation value, the variance is given by this integral. And you will see this is equal to sigma squared. So this sigma squared appears, appears here. Okay. And this mu appears here. So if a random variable follows a normal distribution with parameters mu and sigma squared, then its mean is mu, and its variance is sigma squared. Okay. Now, let's calculate the moment generating function. Okay, what was the definition of the moment generating function? It is the expectation value of exponential of tx, where t is a variable and x is the random variable. Okay, So if you apply this definition to the normal distribution, so this is exponential tx and exponential of x minus mu squared to sigma squared. So if you calculate this, you should have this result. T plus sigma squared t squared over 2. Yeah, you should try this yourself. And of course, you can use this moment generating function to calculate the value of mu and the variance, right? So if you differentiate this function and put t equal to 0, you should have mu. And if you differentiate again and put t equal to 0, then you should have the expectation value of x squared, which should be sigma squared plus mu squared. So if you subtract mu squared from here, you get the variance, which is sigma squared. Okay? And you should also try to calculate this quantity. So x minus mu over sigma cubed. So what was this called? Just called skewness, right? But if you examine the symmetry of the normal distribution, it's immediate, right? What is the value? It should be 0 because it's symmetric around the mean. And you should also try to calculate this quantity. This to the power of 4. What was this called? This was called the kurtosis. Okay, so what is the value of this? So this is not 0 because it's, the power is even number, so it cannot be cancelled by the symmetry. Okay. Now suppose we have a random variable that follows the normal distribution with parameters mu and sigma squared. So that means its density function is this. Okay. Sorry. X minus mu squared over 2 sigma squared. Okay. And now we change variables by this linear transformation. Okay. So new random variable z is defined as this x minus mu over sigma. Okay. Then the question is, what is the density function for z? So since this linear transformation is, of course, linear, and it's also monotone increasing because sigma is positive, so the coefficient of x is positive, so it's just an increasing function. So we can just simply write f of x dx is equal to g of z dz. Okay, so in order to find g of z, we find fx dx dz. Okay, so from this transformation we can solve for x, which is sigma z plus mu. So dx dz is just sigma. Okay, so this will be just sigma. Okay, and f of x is, so we replace x with this, sigma z plus mu times sigma. So this should be the density function of this random variable z. So let's try to calculate this. So we use this f of x here. That's square root of 2 pi sigma exponential. Instead of x here, we use this sigma z plus mu. Okay, plus mu minus mu. So this minus mu is this minus mu, right? And divided by 2 sigma squared times sigma. Don't forget this sigma. Okay, so but this sigma cancels this sigma in the denominator, and this mu cancels this mu. So we have sigma z squared, but we have sigma squared here in the denominator of exponential. So this sigma is cancelled by this sigma. So after all, we have square root of 2 pi exponential of z squared over 2. So what is this density function? This is the density function of the standard normal distribution, right? So the mean is 0 and the variance is 1. So that means if x follows the normal distribution with mu and sigma squared, then if you define z, so do you remember what we call this transformation? So subtract mu, the mean, and divide by the standard deviation. This is called standardization. Standardization of a random variable. Then this new random variable follows the standard normal distribution. That means the mean is 0 and variance is 1. So any normal distribution can be converted into the standard normal distribution. That means if we know the standard normal distribution, we know any other normal distribution. Now, let's look at the same thing from a different angle. Let's say we have the density function for the standard normal distribution. That is this exponential of negative c squared over 2. And let's define the cumulative distribution function for the standard normal distribution. That is, by definition, it's the probability that this random variable takes the value less than or equal to some given value, which is given by this integral. Okay, from negative infinity to small g, z, and phi of z and dz. So this is standard for standard normal distribution. Now, so that means, let's say z follows normal distribution with 0 and 1. Okay. Now, suppose x follows the normal distribution with mu and sigma squared, Then the density function is, okay, I write again and again so you can memorize this. Exponential x minus mu squared over 2 sigma squared. Okay, and its cumulative distribution function, f of x, is, by definition, is the probability that this random variable takes the value less than or equal to x, which is integral of the density function. Okay. Now, again, let's do this transformation. Okay. By the way, this z is a new random variable defined by a linear transformation of the random variable x. Okay. So this z itself is not directly related to this z. Okay. Now, the cumulative distribution function of x is the probability that x takes value less than or equal to some given value of x, right? So this should be equal to the probability that this. So basically we subtract mu from the both sides and divide both sides by sigma. So these two probabilities should be equal. Okay, but this one is just the newly defined random variable z. So z. Okay, so we define this as z. So that is the cumulative distribution function for the standard normal distribution. Now let's differentiate the cumulative distribution function. This, okay. So this cumulative distribution function for x is equal to the cumulative distribution function for z. And we apply the chain rule. Not this. Z. And this is dx. But this part is the density function for the standard normal distribution, and this one, since z is defined as x minus mu over sigma, this should be 1 over sigma. Okay, again, we have the density function for the standard normal distribution as sigma times f of x, but we changed the variable x to z, so x is equal to sigma z plus mu. Okay, so that is 1 over 2 square root of 2 pi sigma exponential and sigma z plus mu minus mu squared over 2 sigma squared. And again, we get the same result, right? This mu cancels, this sigma cancels, because it's squared here. So after all, we have the same density function for the standard normal distribution. So the point is, if we transform a normal random variable by this transformation, where x follows normal distribution with mu and sigma squared, then we can calculate any probabilities related to this random variable x by in terms of the standard normal distribution. Where, of course, z1 is equal to x1 minus mu over sigma, and z2 is x2 minus mu over sigma. So, if we know the standard normal distribution, we can calculate any probabilities regarding any normal distributions. So by using this fact, we can utilize this table of the standard normal cumulative distribution function. Okay, so this table just gives you the probabilities of various values of z. Okay, for example, when z is negative 3.4, and this means, okay, how can I explain this? Negative 3.40, then the cumulative distribution function gives the probability of 0.0003. When the value of z is negative 3.41, then 3.4 and 0.01. So that is this. Not much difference. Let's take another value. When z is negative 2.22, negative 2.22, so this and this, the probability that the standard normal random variable takes the value of less than or equal to this value, negative 2.22, the probability is 0.0132. So that's how you use this. So basically what we are looking at is if we have this density function of the standard normal distribution, you pick this number, and we are calculating the area under the curve from negative infinity to up to this point you have chosen. Okay. So what about the probability of a range like this one? So in that case, if you recall the axiom of probability measure, axiom 3, this can be written as okay, maybe I should use another note. So this probability can be written as probability that z is less than or equal to z2 minus z less than or equal to z1. So that is phi z2 minus phi z1. Okay, so for example, if you want to calculate a probability like, for example, 1.5 z less than, let's say, 0.5. Then you can calculate this as 0.5 minus phi of negative 1.5. So let's look at the table. 0.5 is here, so that's 0.6915, and negative 1.5 is this one, 0.0668. 0.0668. So that should be, let's see, 0.6915, 0.0668. Okay, that should be 0.6247. Sometimes it is very useful, handy to, if you remember some particular values for this, for the cumulative distribution function of normal distribution. This value, for example, the probability that the standard normal random variable is greater than 1 is given by this: infinity minus 1.0, right? And of course, this phi of infinity is 1, and this one you can look up the table and you will find 0.8413, which is of course approximately, which is equal to 0.1587. So that means approximately 16% of the with 16% probability, the standard normal random variable takes value greater than 1. And similarly, greater than 2 is approximately 0.0228. So approximately 2.3% chance of the value being greater than 2. And z greater than 3 is approximately 0.0013. So the chance is about 0.1% for z being greater than 3, and so on. Now let's see one of the most outstanding properties of the normal distribution. Suppose we have a random variable x which follows the normal distribution with mu1 and sigma 1 squared, and x2 that follows another normal distribution with a different set of parameters. Then define y as x1 plus x2. So what is the density probability distribution of this new random variable y? Actually, it turns out this follows a normal distribution with parameters mu1 plus mu2 and sigma 1 squared plus sigma 2 squared. Okay. Of course, we're assuming x1 and x2 are independent. Okay, how can we prove this? Let's see. So let's prove this by using the moment generating functions. Okay, so we have seen that the moment generating function of the normal distribution is given by this. Of course, let's write the definition for the sake of it. Exponential, so it's an expectation value of exponential of tx1 in this case. So it turns out this is equal to exponential of mu1t plus sigma 1 squared t squared over 2. And similar for x2. So I just skip this. That is e2 t sigma 2 squared t squared over 2. Now, we want to calculate the moment generating function for y, which is the sum of x1 and x2. Okay, so that is expectation value of e to the power of ty, but y is x1 plus x2 because it's exponential function here. So we have tx1 times e tx2, but x1 and x2, they are independent, so we can split this expectation value into the product of expectation values. Okay, this is possible because x1 and x2 are independent. Okay, so independence of x1 and x2. Now we know these functions, right? From here. Okay, so that's expectation value, exponential of mu1t sigma squared t squared over 2 times exponential of mu2t sigma 2 squared t squared over 2. Now let's combine these two, and we have mu1 mu2 t plus sigma 1 squared plus sigma 2 squared t squared over 2. But this function here is the moment generating function for the normal distribution with parameter mu1 plus mu2 and sigma 1 squared plus sigma 2 squared, right? So therefore, that means y's moment generating function has the same form as the moment generating function of a normal distribution of these parameters. So y follows the normal distribution with these parameters. Okay. And similarly, if you have more random variables that follow, okay, so x1, x2, xn, so they all follow normal distributions, mu I plus sigma I squared, then define a new random variable as the sum of these normal random variables. Then y follows a normal distribution with mu1 plus mu2 plus and so on up to mu n, sigma 1 squared, sigma 2 squared plus and sigma n squared. So you can prove this by using mathematical induction.